and has appeared in prime time on the BBC's Stargazing Live with Dara O'Brien on The Night Sky, with Patrick Moore, and on the BBC One show. So please welcome Professor Don Kurtz. I just want to say about the break. I just want to say it quickly. So I just want to tell them about the break. Sorry, what I forgot to mention is that there will be no break, so it's going to be a 2-hour lecture. Okay.
Thank you, Midday.
Thank you. I'll see you later.
Let's put that on.
Thank you very much. And they'll be writing to you. You've been sorted with your money.
I'm sorted. Yeah. Okay, thank you, Midday, and good afternoon, everyone. All right, we will reposition it. You're a trustworthy audience for that particular message. What I said was, thank you, Midday, and good afternoon, everyone. We all can immediately hear my North American vowels. I hear them too. I grew up in San Diego in California, and San Diego's got a lot in common with Cape Town. When I was in high school in the 1960s, a cult film came out by a filmmaker named Bruce Brown called The Endless Summer. It was about 2 young American surfers, just the age of us at that time, and they traveled the world chasing the summer, looking for the perfect wave. And they found it at Cape St. Francis, South Africa. That was my first mental knowledge of South Africa, and it sat there in my mind until a little over 10 years later, when I got my PhD. There was the opportunity to come here to the University of Cape Town for 1 year as a postdoc. I did that, but that year stretched to 24. And I've been coming back ever since. I think I've been giving summer school lectures for just on 30 years now. Waves, surfing, waves we know about in Cape Town, and in fact, it's waves I want to talk to you about right now. But for the moment, let's do away with the pretty pictures, folks. It's time for physics. I want you to have some terminology for waves. Here's now a mathematical wave instead of an ocean wave, or it could be ocean. Things we're going to talk about: wavelength, the distance between the crests of a wave, the velocity of the wave, how fast it moves, and for light, that's the speed of light, isn't it? Only sometimes. Most of the time, light travels a whole lot more slowly than that, and that'll be important for this lecture. And then occasionally I may mention frequency. That's the number of waves to pass a particular point in a given length of time. Light is a wave. It's what we call an electromagnetic wave. In atoms, there are electrons, and if the electron moves, if you wiggle a little electrical particle up and down, it sends out a wave of changing electric field. And in this diagram, that's this red wave coming this way. That's a changing electrical field caused by a moving electrically charged particle, like an electron. But a changing electric field creates a changing magnetic field. That's this blue wave. And the changing magnetic field creates a changing electric field, which creates a changing magnetic field, which it's self-propagating. And in empty space, it does move at 300,000 kilometers per second. We call that an electromagnetic wave, and light is just one kind. This color in the open air is what we're talking about today. But for us, we humans, we say seeing is believing. But vision just gives us a window on a tiny piece of what the entire electromagnetic spectrum is. These electromagnetic waves include light waves, but they run from very high energy gamma rays and X-rays, which we use in medicine, down through the visible part to infrared and out into the radio waves. This is all the same phenomenon. Electromagnetic waves, the visible part is just the part we can see with our eyes. And the things that I want you to have in your mind for the talk today is that the color of light depends on its wavelength. And the scale down here is in meters. I'm going to talk in nanometers, which are billionths of a meter. Blue light for us, this purple, has a wavelength of about 400 nanometers, 400 billionths of a meter. Red light has a wavelength as long as 750 nanometers, and of course the other colors are in between. It's also true that blue has more energy than red. We need some terms about what happens to light as it moves from one medium to another. And so in this schematic diagram here, on the top, we're either in air or in a vacuum, and light's traveling essentially at the speed of light, 300,000 kilometers per second. The light wave comes from the upper left, and these are the tops of the waves. These are the wave crests, and hits a block of glass, where it slows down to 200,000 kilometers per second. Now that sounds fast, but it's a whole lot slower than 300,000. And what happens in the process? This end of the wave enters the glass first, it slows down, and the bit that's outside is still going at speed, and so this side overtakes that side, and the whole wave changes direction. The term for that is refraction. So the light wave is refracted because it slows down, and if you look carefully, you'll see the wavelength got shorter, the wavelength got squashed, the frequency's gone up. Sometimes the wave can be reflected at the surface, and then it bounces out. If you draw a vertical, the angle of incidence equals the angle of reflection. There goes some of the waves reflected. And we will talk about reflection. The main thing here at the moment is the refraction, the change of direction, and there's the common experience of it. You've done that with a spoon in a glass. Some of you have got pools, although I hope you're not filling them at the moment because of the water shortage. And when you stick a cleaner in, you can see the way it looks bent, because of the change of speed of light when it enters the water causes the light to look, causes the pencil to look like it's bent. Some of you might be wearing diamonds. I'm sure that's the case somewhere in this room. Light in a diamond slows down to a mere 124,000 kilometers per second. And the light gets spread out into its colors, and that's the next topic. We need another subject here. We need dispersion. When light, here's white light coming from the sun through a hole in a window shade, passes into a prism made of glass, the light slows down, but the amount it slows down depends on the color. Blue light slows down more than red light, and because the blue light slows down more, it's bent through a larger angle. And so the light is spread out into its component colors, and that is called dispersion. We tip the glass at opposite angles here for a prism, and that makes it spread even further when it comes out, and we end up with our natural spectrum in the visible part of the electromagnetic spectrum where we can see. Let's put it to some use. That's the background. We just got refraction, the bending of light, reflection, the bouncing of light, and dispersion, the light being spread out into its colors. There's a picture I took in Kruger Park sometime in the last couple of years. And, well, all right, it is of a glossy starling, but for the moment I actually want you to look at the blue sky, then we'll come back to the starling. Why is the sky blue? Light passing overhead, if there were no air, the sky would be black. And in fact, we'll come back to that. The sky is black on the moon. The moon has no atmosphere. But here on the Earth, light passing overhead is passing through the air, and the air is full of aerosols, small dust particles, little globules of liquid, and the typical size of the aerosols in the Earth's atmosphere is about 300 nanometers. That's just slightly smaller than the wavelength of blue light. And the consequence of that is blue light scatters much better than green, green scatters much better than red. So when you look up overhead at the sky, most of the light continues, but the light that does get scattered is predominantly blue. Now, if you can understand that little bit of physics, you can now understand why this glossy starling's blue. Evolution is wonderful. And what it's done in the case of the starling is the bird's feathers have evolved little pockets, little vacuoles. They're air-filled, and they're about 300 nanometers in size. And they scatter blue light much better than the long wavelengths. And so the bird is iridescent blue for the same reason the sky's blue. Our sunbirds, of course, have got beautiful colors. Many of them double-colored, orange-breasted, malachite here on Table Mountain, are bright green. North American hummingbirds do the same thing. The bird that's iridescent green has got those same small vacuoles in its feathers, but then it has the pigment melanin, the same thing that makes skin dark, and that blocks the blue, so the green is the next thing to come through. Remarkably, if you look at this hummingbird with its beautiful iridescent colors on its body, notice the wings are rather dull. This little bird is really small, and it needs a lot of power to fly the way they hum, and those air pockets would in fact make the flight feathers not strong enough if they had air pockets, and so the bird's not iridescent on its flight feathers. Some of the bigger ones, like a malachite sunbird, can manage that, and they've got air pockets in their feathers. So we've got a blue sky and blue birds, because these little air pockets or aerosols scatter blue better than red, and it even happens on a scale way beyond the size of a star. Here's the Pleiades star cluster. Tonight when you go out, if you look up at Orion and follow the belt of Orion to the left to the bright red giant Aldebaran, and just beyond that in Taurus the ball is the Pleiades. All cultures have got the Pleiades. Everybody knows what the Japanese call the Pleiades? Subaru. Look at the plaque for the company. In Zulu, Xhosa culture, the Pleiades are Isilimela, and when they first appear just before sunrise is the time of year when the young men go through their initiation ceremonies. That's important in local culture here in South Africa. This blue light you see is dust between the stars, and the dust particles are about 300 nanometers in size, so they scatter blue light better than they scatter longer wavelengths. So the blue sky, the blue birds, and blue on the scale of an entire cluster of stars all comes from that basic, simple concept of scattering off of small particles being dependent on wavelength or energy of particles. I love this picture. I hope some of you have seen it before. This was taken by the Cassini mission, which is still orbiting Saturn. It is soon to be crashed and destroyed at the end of its life. Oh, shame, having to sit on the stairs. Let me just look around. Are there any seats in here? You know, if you want to look for, let me digress just a bit. Back in the 1870s, when Mark Twain was a young man, he was well known, but he wasn't recognized. And he was giving a talk in a town one night when he rode in on his horse, and he went over to the barber to get his big mustache trimmed up, and the barber said to him, "Well, stranger, y'all are real privileged to arrive here today, because this here Mark Twain's talking tonight. As soon as I finish with you, you better go get a ticket, because it's going to be standing room only." And Twain looked up at him, smiled, and said, "Darn, seems I always have to stand when that man speaks." Well, I do need to stand. You're sitting, but there is one more chair there if somebody wants to sneak into it. Oh, sorry, it's broken. Okay, and there's one right in the corner there. All right, back to Saturn. The Cassini mission was on the other side of Saturn. This is 1.5 billion kilometers out in the solar system, looking back at the sun, which is behind Saturn, and the dust and moons, little tiny moons that make up Saturn's rings, kind of scatter bluish light. You can see the blue color. These rays you see are reflections inside the camera. They're not real. But the real gem in this picture is right there. That little blue dot. That's us. There's the Earth from 1.5 billion kilometers away. And look at the blue from the blue sky and the blue oceans. We'll come back to why the oceans look blue. If you look at Saturn in the right direction, it also scatters blue light. This is a bit saturated, but the wavelengths are right, and that's from the Cassini mission. All these bands you see here now are the shadows of Saturn's rings with the sunlight filtering through them down onto the gas that makes up Saturn's atmosphere. On to sunsets. I took this picture just a few months ago in Malawi. My wife and I had a little holiday, and we were on an island called Mumbo Island just off of Cape Maclear. And there was the sunset from our cottage looking out over Lake Malawi. Why is the sunset red? And the answer is the sunset's red for exactly the same reason the sky is blue. Here's a real picture of the Earth from space. Glorious picture. There you can see a cold front came through Cape Town a few days ago, and there's another one coming. But can you see the Earth's atmosphere along the edge here? And the answer is no. The Earth's atmosphere is incredibly thin. And so having told you that, I've greatly exaggerated it in this very basic diagram I made. So the atmosphere is way too thick. This is not to scale. But when you look up through the atmosphere, we use a term, we say you're looking through one air mass. When you look over at the horizon at the sunset, with the very thin atmosphere, you're actually looking at up to 35 air masses. So what's happening? The light's passing through the air, and the blue light's getting scattered away. And the more air you look through, the more blue gets scattered away, and then you end up with the red left behind. You end up with the red sunset. So red sunsets are red for the same reason the blue sky is blue. It's the scattering of light that depends on wavelength. Down in Lakeside, there's a little B&B. This is Cape Town. Shot that a couple days ago, Blue Moon. And of course, that's the title of this talk, Once in a Blue Moon. Picture of a real blue moon. No. This is photoshopped. I do want to tell you the truth all the time, folks. I hope I don't fail. And when I take something that's been photoshopped, I've got to tell you, that's just been colored blue by somebody in a computer. But there really are blue moons. From about the 1940s, people started calling the second full moon in a month a blue moon. I find that concept incredibly boring. If you were Muslim, there would be no second full moon in any month. If you're Jewish, there's no second full moon in any month because the month is the length it takes the moon to go through its phases. That word month comes from the moon. It's a month. And it's only because in the Gregorian calendar we've juggled our months long and we've made some of them 31 days when it takes the moon 29 and a half days to go through its phases, that occasionally you get a full moon on the first of the month and then another one before the end of the month. Is that interesting? Well, is it interesting when the odometer in your car turns 111111? Well, okay, but it's pretty predictable, isn't it? I'm not excited by that, but there are real blue moons, and that's where the expression comes from. Occasionally, after a volcanic explosion, 1991, Mount Pinatubo in the Philippines made the skies go really weird here in Cape Town. My observations at Sutherland were really fouled up by that for 6 months. After a big forest fire, you can get aerosols in the air where the particles are all of a fairly uniform size and they're roughly 1 micron in size, which is 1,000 nanometers. They're a little bit bigger than red light. And then the sky scatters red light better than blue. And I have seen faintly blue sunsets and moonsets back at the time of Pinatubo. And so there really is a blue moon occasionally, only once in a blue moon. That's where the expression comes from. Red moons are real. That one's not photoshopped. Well, it is in the sense the 3 moons have been piled up. These are 3 exposures of a full moon going through the Earth's shadow during an eclipse of the moon. Well, if the moon's in the Earth's shadow, the Earth's blocking the sun, why does the moon have any light on it at all? Schematically, here's the answer. This is not to scale. Oh, let me get it to scale. If I shrink the sun down to the size of my head, the Earth is a little less than 1 millimeter in size, and if my head's up here at the front of the room, the Earth's back to back. This is not to scale, not even close. But it gives you the idea. The light from the sun is blocked by the Earth. The Earth has a shadow in space, and the moon passes through that shadow. And you would think at first look that the moon would go black because there would be no light on it. But that very thin atmosphere of the Earth refracts light through it. The light's bent, and it's bent into the shadow. And what kind of light gets into the shadow? The blue gets scattered away. It's the red that's left over, and that leaves us with these lovely reddish lunar eclipses. And if you've seen eclipses of the moon, everyone's different. It depends on how much dust and smoke and other things are in the atmosphere around the limb, what color the moon turns during an eclipse. What color is the moon? Silvery, golden. Oh, supermoons. We do have to talk about that, but the moon's black. That's a real picture. This is not Photoshop. That's taken by an Earth observation satellite looking back at the Earth as the moon passes in front of the Earth. The moon's covered in basaltic lava. It only reflects the amount of light that coal dust reflects. It's black. Why does it look white in the sky? Well, because the sky around it is really black. There's nothing coming from that. You just don't have good contrast. So the moon looks this brilliant white in the sky, but it's in fact, it's just reflecting sunlight and not very much of it. By the way, because you're looking from outer space down at the Earth from beyond the moon, you're seeing the other side of the moon. This is the bit we never see from the ground. That's not the dark side. There is no dark side of the moon. The whole moon has a day and the sun rises and sets, but it's the far side that we can't see. Here's an astronaut. Oh, now you saw in the news last week, Gene Cernan died. He was the last of the astronauts who stood on the moon who was living, and he's gone now. So nobody is left alive who ever stood on the moon. It's time to go back. There's an astronaut standing on the moon. You can see how dark the ground is. The sun's reflecting off of his white spacesuit. He's wearing very fashionable platform shoes, which were all in fashion in the early 1970s, but he's wearing them for a practical reason. Let's take a hot summer's day here in Cape Town. It's going up, what, to 30 tomorrow? All right, tomorrow when it's 30 at midday, noon, the tarmac has been heating, and maybe your feet are still tough enough, but go stand on the tarmac in bare feet. Ground temperature here on tarmac will get up to 50 or 60 degrees in the middle of summer in a place like this where the sun's high. Why doesn't it get hotter? Because the air heats, the hot air rises, and it carries the heat away. The moon has no atmosphere. It's the same distance from the sun, and where he's standing there, the ground temperature is about 100 degrees Celsius. And so those platform shoes have got a very practical purpose. The sky's black behind him, but not to him. The photographer who took this picture was exposing the picture for the bright white of the spacesuit, for the light reflecting on this American flag that had been placed there on the moon. It's not blowing in the wind, by the way. It's just hanging from something. It's crumpled. And the astronaut, who's got better contrast, would see something like this. Now, this is photoshopped. This is not real, but it gives you an impression. Even during the day on the moon, these astronauts, when they look up, can see the stars just as well as you can see them at night. The stars are always out for somebody standing on the moon. Shifting back to blue, there's a picture of a fisherman sitting on a Makoro in Lake Malawi, and there's beautiful blue Lake Malawi. A clear blue mountain lake. It's a cliche, a clear blue mountain lake. Why are lakes blue? Is water blue? Well, there's the same lake looking in another direction. And now it's a green lake. And in fact, Lake Malawi is green around the shore. There's my wife snorkeling, and the water's green. And notice you can't actually see out of the water. Water has got something called a critical angle. In this diagram, in the water, the light is coming up towards the surface, and when it changes from water to air, it speeds up, and so the path changes. That's refraction. And there you see the path change as the light comes out. If light were coming in, the same kind of thing would happen. But there's an angle, a critical angle, which is 46 degrees, and when the angle is more shallow than that, you get total internal reflection. None of the light gets out. It's all reflected and stays in. And in fact, that's what we saw in the previous picture, where my wife's floating around snorkeling, and you can see reflections of her, but nothing outside. That's total internal reflection. You can get total external reflection too, and that's what's happening with the fisherman sitting on the lake. We're looking at a low angle, and it's the blue sky that's reflecting in the lake, and you're not seeing the blue of the lake, you're seeing the blue of the sky. It's a reflection. We use that technologically with fiber optics. Fiber optics is a clear glass or other substance, very, very thin. We put light in one end, and it's designed so that the angle of reflection inside can never be more than the critical angle. You get 100% reflection, and the light bounces around inside this optical fiber no matter how it's bent and comes out the other end. And at least where I live in England, that's how my internet comes to my house, on optical fiber, because the light waves have got very high frequency, much higher frequency than radio waves. And since you're carrying information by modulating the frequency, FM, or modulating the amplitude, the height of the waves, AM, you can pack much more information into a light wave than you can into a long wavelength radio wave. And so fiber optics coming here too. You'll get those and your internet will speed up. Let's go back to the sunset. There's a nice red sun setting. You now know why sunsets are red. You can see the horizon right here. You can see the division between the water and the sky, and you all had that experience. You walk over to the west coast, you watch the sunset from Camps Bay or from Llandudno or from the top of Lion's Head, and there's that lovely horizon between the sea and the sky. And now the question for you is, why can you see the horizon? Where the light is hitting the ocean out at the horizon, it's hitting at an angle of nearly 0 degrees. There should be 100% reflection. And the sea should just reflect the sky, and they should just blend into each other. Well, in fact, they do in certain circumstances. I've stood on the seashore in Trieste in Italy on the Adriatic, where the sea is utterly calm, like a mirror, and it is a mirror, and you just see the sky reflected. You can't see where the sea stops and the sky begins. The reason you can see the horizon is because there are waves, and there's never not waves around the Cape Coast. This is the Cape of Storms, amongst other things. We've always got seas. And so with those seas out here, when the light hits, the wave's tipped up, and now it's not getting reflected to you. It's getting reflected somewhere else, and only a bit gets reflected to you. And the net effect is that the sea is always darker than the sky, and you can see that nice sharp horizon. Now, all these little bits that are tipped, each one of them potentially can act like a mirror. If the sea were absolutely flat, you'd just see an image of the sun in it. It's like a mirror. But in this case, all of these little bits are acting as individual mirrors. You can see the little spots here, and some of them tip at the right angle temporarily to send the light to your eye. This is called a glitter path. And the width of the glitter path depends on how big the waves are. The bigger the waves, the fatter it gets. You can judge how rough it is out at sea by looking at the width of a glitter path. When the sun gets very near the horizon, then the angles get so low that none of the waves can reflect light to you. And if you go watch a sunset sometime, you'll see the glitter path disappears before the sun goes down. This is a real picture, and this is a case where the water is utterly still. And indeed, there's your reflection. There's the reflection of the sky. And that's what the sea would do if it were flat. Well, let's imagine going to lakes somewhere else in the universe. Here's a little moon called Io. Io orbits about Jupiter. Io is about the same size as the Earth's moon, and Io will appear in the next talk when we get to tides, because tides are really effective on Io. But for the moment, what I want you to notice is Io, this is not some sort of cosmic pizza. This thing is covered in volcanoes, and the volcanoes erupt, and they mostly erupt molten sulfur. And there are molten sulfur lakes on Io, and that black thing you see right there is in fact liquid sulfur. What color is liquid sulfur? It's the same color as the solid sulfur here. It's reddish yellow. Why does the lake look black? Because if you were standing on the edge of that lake looking at that liquid surface, it would be reflecting the sky just like this. So there's a clear black lake. The moon has no atmosphere, and its lakes will appear black. We might imagine on other planets elsewhere in the universe, I'll talk to you about those just briefly during these two talks, that there are going to be some very strange and wonderful places to see that are different from the Earth. Outtake from the first Star Wars movie. Here's the fictional Luke Skywalker walking off onto his planet called Tatooine in the film, after, in fact, a town in Algeria. Tatooine supposedly orbits a double star. Two stars orbit each other, and the planet orbits the double star. Could this ever happen in the real universe? And the answer, oh yeah, we found them. With the Kepler mission, we found dozens of what we first started calling Tatooines. We now rather more prosaically call circumbinary planets. And some of those planets look like they might be habitable. And so if life is common in the universe, we don't know. That's an unanswered question. But if it's common, somewhere, somebody out there gets to watch double sunsets like this. Wouldn't that be a fun place to live? What does a sunset look like on another planet? There's another planet. This is not Photoshop. This is a real sunset on another planet. This is the planet Mars. We are there with rovers that are wandering around on the surface that can take pictures. Mars's atmosphere has a pressure of only 1/100th the pressure of the air you're breathing right now. The atmosphere is thin. It does scatter blue light better than red, and so why does that sunset look blue instead of red? And the answer is the atmosphere is so thin it's not scattering much, so you're not noticing the sun go red, but what you are noticing is that near the sun where it's brightest is the only place where there's enough light that some of the blue light that gets scattered appears, and so the whole sky is blue, but you can only see the blue very close to the sun where the light's brightest. There's a comparison between the Earth and Mars set to the same scale. There's an earthly sunset. From Mars, being 50% farther from the sun looks 50% smaller. Look at how much smaller the sun looks in the sky. And of course, on Mars, you don't get these beautiful red sunsets that we get here. Now, this next picture is a real picture, and this was taken by an alien spacecraft. We are the aliens. This is from the high-res camera on the Mars orbiter, and 2 weeks ago it released a picture it took of the Earth and the Moon. So they turned the camera that's supposed to be studying on Mars back on us and took this picture from Mars. And all right, it's a bit low resolution, but isn't that phenomenal that you can now look back at us from other places in the solar system? With the Kepler mission, that's where my prime research is, but my research is in this field of astroseismology that Mayday mentioned at the beginning. I'm studying vibrations in stars. We use that to understand the planets. The mission has found 5,000 planets around other stars. We have now concluded that virtually every star's got planets. That's the norm. And we're now beginning to imagine what those planets would look like, and we're getting some information about them. Most planets in the galaxy, probably most stars in the galaxy, are going to be like this artist's impression. When we look out in our galaxy, almost all the stars are tiny little red dwarfs. Now, you can't see them with your naked eye, but with our telescopes, we see that. They're a tenth the size of the sun. They're much fainter, they're much cooler, and they're the ones where we're finding the planets. Here's an artist's impression of what it might be like to live on such a planet with this very red light coming from this cool red star, and on the ground, you've mostly got red light. You know, you and I don't see red very well. I see it worse than you do. I'm partly red colorblind, but that's not my point. If you're driving out on the motorway and it's foggy, what kind of lights do you use for the fog? You use yellow lights, because yellow gets scattered less than blue. We're back to the scattering, and the yellow will penetrate further into the fog. Red will penetrate even further. Why don't you use red fog lights? And the answer is you don't see red very well. So if we go to one of these planets, we wouldn't see so well, but we can easily imagine that if there's life on those planets, life will evolve the ability to see in the red and the infrared. And here on planet Earth, that's already happened. There's a couple friends of mine, North American rattlesnakes, and they have evolved pits in their face here, which are infrared eyes. Why? Oh, as you sit there right now, you're hot stuff. At your body temperature, 311 degrees absolute, 37 degrees Celsius, you're radiating about 100 watts out into the room. Now, the 200 of us in here, 200 times 100, we got 20,000 watts of heating just came in. Maybe it's the reason they keep the air conditioning so high. And you're radiating in the infrared. That snake can see you in the dark by the light you shine by. That's not interested in you. It's interested in the little mice that it eats, and they shine too. And all I'm saying is that we have got we've got vision in the visible, because that's where most of the light from the sun is. We've evolved eyes to see what's there. Animals evolving on a planet around a red star would evolve eyes that would see in the red and would be able to see. Now, remarkably, just within the last 6 months, a planet which is potentially habitable and might have liquid water has been discovered around the closest star to the sun. It's called Proxima Centauri. So here's a view of the sky, not so different to what it'll look like tonight when it gets dark. This happens to be in Chile with one of the big telescopes at the Cerro Tololo Observatory. Here are the two pointer stars, Alpha and Beta Centauri, pointing up to the Southern Cross. This should be familiar territory for lots of you. But Alpha Centauri is actually a triple star. And if you look with a big telescope, you can see Alpha Centauri is a pair of stars orbiting each other. The brightest one's very much like the sun. Now, I'm going to digress slightly right here. These big spikes that you see are artificial. The stars don't have spikes on them. That comes from another term that we haven't talked about yet. It's called diffraction. We've had refraction, reflection, and dispersion. That comes from diffraction. That's light, which is a wave passing by a barrier, in this case, the arms that hold up one of the mirrors in the telescope. And because of the wave nature, as it passes by the barrier, some of the energy goes into the shadow of the barrier. And that artificially produces these diffraction spikes because of the way we build our telescopes. I'll mention diffraction just briefly for a couple of things we'll look at in the atmosphere. Orbiting about the two stars of Alpha Centauri is Proxima Centauri, which is way over here, and it's a little tiny red dwarf. You need a big telescope to see that. It's 10,000 times fainter than the faintest star you can see with your naked eye. It's a little red dwarf, and it's the closest star to planet Earth. And just last year, around that was discovered a planet in the habitable zone where water could be liquid. That star is so faint that the planet orbits the star in 11 days. It's got to be up close to be warm. We've got a 365-day orbit around the sun. This planet's got an 11-day orbit, and here's the artist's impression of what it might look like. This is guesswork now. Where are we going with this? Well, this is what it might look like with the red star here, and then off in the distance there's Alpha and Beta Centauri, the two much brighter ones further away, and the red light lighting up the landscape. With those 5,000 planets, what we're planning to do is use big telescopes under construction. The European Extremely Large Telescope, it's under construction in Chile. Cost is 1.2 billion euros. It's being built. James Webb Space Telescope to be launched next year into space, 6.5 meter diameter mirror. It'll be orbiting beyond the moon. It'll have infrared cameras on it, and it should be able to see the planet separate from the star. Now, when I mean see, I don't mean image the ground, but we will be able to see the light, look at the spectrum, and determine what the atmosphere of the planet is made out of. Here on Earth, the 21% oxygen you're breathing right now, that's produced by life. That oxygen didn't exist until about 600 million years ago, and then the oxygen got pumped up in the atmosphere by plant life, and that's when we got the Cambrian explosion. That's what made it possible for so many different life forms to evolve, ultimately for us to be here. If we find a planet with oxygen in the atmosphere and methane, we've got methane in the Earth's atmosphere, that comes out of the termite mounds here in South Africa and out of the front end of cows all over the world. And it's not stable. Methane and oxygen oxidize. It doesn't last. You need to keep pumping the methane in. If we find a planet that's got methane and oxygen, probably there's life there. And that is likely to be the announcement you'll hear in the next 10 to 20 years when you read in the news one morning, there's life on another planet. If that comes, I think there's a good chance. What will have happened is we will have found a planet that's got an atmosphere with nitrogen and oxygen and methane and water vapor like the Earth, and we will presume that means there's life there. We won't have seen it directly. Back to Cerro Tololo for another purpose. This is now a time exposure, looking west, watching the stars set as they come down. Now, if you take a vertical, the angles that the stars set to the horizon is equal to your latitude. If you were on the equator, the stars would go straight down. If you were standing on the South Pole, as you turn, the stars would just go around parallel to the horizon. They wouldn't rise or set. Here in Cape Town, 32 degrees south, same as this observatory, stars come down at an angle of 32 degrees to the vertical, but because the atmosphere has layers in it, and the layers have got different temperature, the refraction's variable in these different layers, and it causes the star trail to wiggle all over the place. That's an effect of all these different layers, and you can see it in sunsets. I hope occasionally in your life you've watched a sunset and seen it go all ripply like this. This is a warning to you. It's a promise to you. If you're watching a sunset like this, watch closely, because this is where the opportunity comes to see the green flash. There are green flashes, and these are the conditions where you're most likely to see it. The refraction in the Earth's atmosphere spreads the sun out into a little spectrum. There is dispersion. And the red sun's on the bottom, and the green sun's above that, and the blue sun's above that, but it's only a tiny shift. And so as the sun goes down, the last little bit left, if there's a little bit left, just as it blinks out, is what's left of the green image of the sun. And you can occasionally see a green sunset like that. From Chile and South Africa, it's Chile and South Africa. From Chile and South America, I've stood on a mountain there at sunset and watched sunsets where I've seen a dozen green flashes on the same sunset as little bits keep breaking off through different layers of the atmosphere. You just have to look carefully. A great place to watch for this top of Lion's Head, or if you're fast coming down Plotaclip, top of Table Mountain, just after sunset, run down. Oh, I used to do that when I worked here. We used to go out after work and zip up India Finster and go around on Fountain Ledge, watch the sunset, and run down Plotaclip. Could do that before it got dark. Right, Ray? All right. Sunbeams. There's a picture I took in Monterey, California, a couple of years ago. I was going to a meeting in Santa Barbara, a NASA meeting for Kepler mission. Driving down the California coast, just the scene caught my eye, and I thought I'd take this picture for you then, because it illustrates something very nicely. You see the sunbeam going off to the right, sunbeam going off to the left? Those sunbeams are parallel to each other. They're not spreading out. The sun is far away. Remember, if my head's the size of the sun, the Earth's a little less than a millimeter in size at the back of the room. All the sunbeams are coming straight at you. And they only look like they're going apart because of parallax. They look like they're spreading for the same reason the road looks like that. You know that road is not getting wider at the front of the picture. It looks narrower back here and wider here simply because it's spreading towards you visually because of parallax, and that's just what's happening with these beams. Those are really parallel. So when you see these lovely crepuscular rays, which is what they're called, shadows of these clouds apparently spreading out, they're really parallel to each other, and the proof is when you see this next time, turn around and look the other way, and sometimes you can see them coming back together in the other direction. Those are called anti-crepuscular rays. I'm giving you a lot of tidbits right now. There's the shadow of a mountain It happens to be full moonrise. That mountain is Mauna Kea in Hawaii, and I occasionally go to Hawaii observing. I was last there 3 years ago in June, which is northern summer, and it snowed heavily. That's the paradise of Hawaii, and you get snow in the middle of summer at an elevation of 4,200 meters. It's cold up there. Well, all right, Mauna Kea is a volcano, but every mountain in the world produces a shadow that looks like a pyramid. It's got nothing to do with the shape of the mountain. You go up on top of Table Mountain and walk over on the west side. When the sun goes down, you look off to look towards the Hottentots Holland and look at the shadow of Table Mountain, and it will come to a point out towards the Hottentots Holland. Because of parallax, the same thing you just saw with those sunbeams. This shadow of the mountain is stretching out beyond the moon before it finally comes together. And so these are really parallel shadow lines on either side of the mountain, and any shaped mountain will do that. And because the moon's actually off to the side, you might wonder why you can see it since it's in the shadow of the mountain, but it's 384,000 kilometers away, and by the time the shadow gets out there, it's a tiny little thing. Even if it hits the moon, it doesn't change what it looks like. All right, you've all seen rainbows. You've stood with friends, family, other people and seen rainbows, but you didn't see the same rainbow they saw. You've got your own personal rainbow. If somebody's standing next to you and sees a rainbow, it's not quite the same rainbow you're seeing. There's a primary rainbow and a secondary rainbow, and we'll have a little mantra here: red on the top, blue on the bottom. The other one, red on the bottom, blue on the top. But for the prime rainbow, red on the top and blue on the bottom. Well, here in this little diagram, some person standing here, the rainbow is always in the direction opposite the sun. The sun's behind you. And the bow is at an angle of 42 degrees for green light from the point exactly opposite the sun. For the secondary bow, it's 51 degrees for green light. So there's the angle. But the only reason a rainbow's a bow is because the ground gets in the way. If you were up in an airplane looking at a rainstorm, it's a rain circle. You'll get the full 42 degrees all the way around at the anti-solar point with red on the top, blue on the bottom. If there's ground in the way, then you get the bow. And of course, you can get a partial bow if there's a rainstorm that's not complete. So what's happening? Here's all the things we've been learning. The white light comes along and hits a water droplet, and the water droplets are roughly spherical. The surface tension pulls them spherical. You can imagine that this water droplet is in fact a prism right here. Just let's draw some points on it. It's a prism. The light hits the water droplet and it slows down in water. Slows down, so it's refracted. It changes its direction, and it's dispersed. The blue light slows down more than the red light until it gets to the back of the water droplet where it's reflected. It bounces and comes to the other end, and it's spread out with blue light on the top and red light on the bottom. What was our mantra? The rainbow has red on the top and blue on the bottom. The light that comes out of the droplet has blue on the top and red on the bottom. Maybe I don't know what I'm talking about. No. Every single color is coming from different water droplets. This is totally not to scale, but it will give the idea. Here, this cartoon man is looking up at the red on the top of the rainbow. The light that went into those water droplets up here, the red has come out to his eye. All the other colors are passing over his eyes higher up. And to see the blue, he has to look down lower where the angle is sharper because the blue's bent more. It slows down more. And down there he sees the blue, and the other colors are hitting him in the face or down on the chest. So the red on the top, blue on the bottom is because blue comes out on the top and red on the bottom of the droplets. And all the colors are coming from different drops. Your rainbow comes from one set of water droplets, and whoever's standing next to you is looking at another set of water droplets. And theoretically, if the storm was really sharp and you had raindrops in front of you and that person didn't, you could see a rainbow and they wouldn't. Usually the storm's not quite that sharp, but it's possible. Now, most people don't see halos as often as they see rainbows, but halos are in fact very common. And particularly here in Cape Town, when I lived here, I saw them very frequently. Normally 1 to 2 days before a cold front comes through, it will be preceded by very high cirrus cloud. Why did I see it so often? Because I hated that cirrus cloud when I was up at Sutherland, because it ruined my observations on it. I kept an eye on it. And if you look up into the cirrus, you've got to block the sun with your hand, otherwise you're blinded. But if you block the sun with your hand looking into cirrus cloud, then you can frequently see this 22-degree halo, which has a faint reddish inner part to it in this thin cirrus light, thin cirrus cloud. Well, there's a beautiful picture of an ice cave in Iceland, and you can see it lets blue light through. But we're not worried about the color of ice. Ice is basically transparent. And here in a schematic is the shape that ice crystals take. Now, you all know that snowflakes, at least you know from pictures if you don't know from experience, you don't get a lot of snow here in Cape Town. Snowflakes are hexagonal. They've got a symmetry to them, a six-sided symmetry. The ice in the ice crystals in cirrus clouds freezes into flat hexagonal plates, and those can grow into long pencil-shaped hexagonal ice crystals. And the light passes in one side and out another, or it passes in the end and out another side, like this, and it slows down and it's dispersed. And so out of the other side comes a little rainbow. As the ice crystals turn and spin in the air, they've got a preferential angle that they send the light out to, which is 22 degrees. They send some light further, but most of it out to 22 degrees, and that produces the 22-degree halo. And there, from Norway, is a nice picture in ice crystals low in the sky of the sun. The 22-degree spots to either side, there's the 22-degree halo. And close to the ground like this, those long ice crystals tend to fall vertically. They're like little fingers. So mostly they're spreading the light out to the side, and you get a concentration here, and we call those sundogs. The technical term is parhelia, with the sun. Sundog because they dog the footsteps of the sun. As the sun goes down, the sundogs go down with it. This is a sun pillar. This is not an artificial diffraction spike. That's a pillar. I'll tell you about that in just a minute. But here's the kind of things you can see if you watch the sky. You can see sun pillars reflecting off of ice crystals. In fact, what's happening with the pillars is you get the flat ice crystal plates, and they tend to float horizontally, and they reflect light off underneath them or from the top of them. And it's exactly analogous to the glitter path across the sea. This is a glitter path across the ice crystals in the sky. There are the sundogs. The arc from the sundogs can actually extend right around to the other side of the sky and come back again. That's called the parhelic arc. The 46-degree halo comes from the light going in the end of the tube and coming out aside. That produces a much fainter halo. I don't see that one very often. And then you have some very rare arcs like this periarc and this circumzenithal arc. I've seen a circumzenithal arc once in my life. There's the picture of it. My wife was having a family reunion at her uncle's house in Sussex, and I looked up at the sky, and there was just the most beautiful circumzenithal arc. I'm not sure what her family thought. I got rather excited about it. The sun has to be between 11 and 26 degrees of the horizon. It can only be in this low position, and in that low position, this points directly overhead, and then towards the sun, you can get this rainbow, the circumzenithal arc. That's the only one I've ever seen in my life. But watch for them, please. They do happen. Well, all right, kite surfing is a big deal now here in the Cape. This is not Cape Town, but there you see the sun pillar, those ice crystals reflecting light off the bottom. Here's a picture given to me by Lawrence Elton just last week that he took on top of Table Mountain. Lawrence, you're here somewhere, I think? Oh, there you are. Good. Thank you for your picture. This is of a glory, and in this case where Lawrence's shadow is showing in this glory up on Table Mountain, it's called in European culture the specter of the Brocken, from the Brocken Mountain. But here's the specter of Table Mountain. Sorry, there's the specter of Table Mountain who took the picture. And glories are not fully understood, but what's happening here is off of little tiny water droplets, the light is being diffracted. The wave nature is causing it to curve around the edge of the droplets. It's being reflected in the back, and then it's interfering. Light is a wave, and if a light wave coming from here and a light wave coming from there arrive at the same place at the same time, so they pile up on each other, they're bright. Whereas if a wave arrives with one up and the other down, they cancel. Surfers know all about that. You go surfing out here, you've got waves coming from different directions. They have different wavelengths. And after a while, all the waves pile up and you get a good set. And then you have to sit and wait while the sea goes flat because the waves don't pile up. What's happening here is for each of the colors, the angle's different. The waves pile up and you get nice bright rainbow. And then they don't pile up, and farther out they'll pile up again and you get a series of rings like that. That's an indication that you're looking at interference. The place you would commonly see this, if you travel, is from an airplane. Often coming in, landing in the fog, you can see that. Person who took this picture, I don't know, I took it off the internet, but they were flying economy. The sun has to be behind you, and you can see that dead center here, somebody's sitting in the back of the plane. It's my common seat too. I presume for most of you that's true. This is called the Heiligenschein, the holy shine. You can see this almost any time. If you get up in the morning and the grass is damp, sorry, if you've got any grass, all right now this is maybe not the right thing to say to you. But grass, bush, if there's some dew on the plants on the ground, and you turn around and look, you will see a glow around your head. And in this case, the photographer has pushed the camera to the side. Notice the glow's around the camera, not around the head. So if you're standing with a friend, you're the only one with a halo. Your friend doesn't have a halo, but he or she sees exactly the same thing. All that's happening is that the light going into the water droplets on the grass is most likely to be reflected right back in the direction it came. And that effect has substantial use in astronomy. Here's a picture taken from the moon by an astronaut who's got the sun behind him, and look at the glow around his head, because the light is reflecting straight back, and you get this very bright glow around his head. Well, that's got everything to do with full moons and so-called supermoons and all that sort of nonsense. Why do I say nonsense? There's a beautiful picture taken by the astronauts coming back from the very first moon landing. Michael Collins only got to orbit the moon. Of course, Buzz Aldrin and Neil Armstrong went down onto the surface. The full moon's beautiful and the full moon is bright, and you've been reading in the news. I heard that there were just absolute traffic jams and nobody could get near Lion's Head for some supermoon last month. Oh, that's just been invented recently, and it's not actually very interesting. The moon is in an elliptical orbit about the Earth. We're going to talk about that in the next lecture too. And when it's closest, it's about 15% bigger in diameter, so maybe 30% brighter than when it's furthest. The moon is at its closest point to the Earth once every month. It does it every single month, but it doesn't often do it at full moon. And so the supposed excitement is that at full moon it'll be much brighter. Now, because of that opposition effect, the full moon is vastly brighter than a first quarter moon. First quarter moon, when you see just half the moon lit, 1 week later the moon is fully lit, full moon. The full moon's 12 times brighter than the first quarter, not twice as bright, and that's because the light gets reflected directly back from a full moon. Full moons are bright. On the horizon they look big, that's an optical illusion. Very few of you are ever going to notice if the moon looks 15% bigger this month than last month when it's on the horizon, because the optical illusion dominates. And will it be brighter? It depends on how many fires are burning. That happens here in Cape Town, how much water vapor there is in the air. And so the next time somebody says there's a supermoon, please do go out and watch it, because any full moon's beautiful, but don't expect you're going to see some spectacle that you've never seen before in your life. This is really overhyped. Some more rare events. These nacreous clouds occur in clouds that are up at about 25 kilometers. And you see this beautiful glow, usually after sunset. The sun's gone down, it's getting dark on the ground, but way up there the sun's still shining. And this is also a combination of diffraction, reflection, refraction. There's a lot of things going on small water droplets, and the different sizes end up producing some very beautiful colors. I've seen similar clouds to that in very high winds above hills in Kruger Park even, so you don't actually have to be near the Arctic or Antarctic, but this is more commonly seen farther from the equator than we are here. One of the places you can see it is in the exhaust trails of rocket launches, because they go so high. And so there's a rocket launch. The sun's already gone down, and there you can see the beautiful color of the sunlight still shining on the very poisonous rocket vapor. That's not good stuff. And coincidentally in this picture, the shadow from that happens to be hitting the full moon. That's entirely coincidental, but it makes for an interesting picture. This is called the zodiacal light. And South Africa is a really good place to see it, and an especially good place to see it in South Africa is Sutherland, the Cedarburg, Namakwaland. Just get away from the city lights. Watch just after sunset or just before sunrise. When it gets dark, you can often see this pillar of light reaching up into the sky. When it happens in the morning in literature, it's called the false dawn. And what's happening there is sunlight is reflecting off of dust between the planets. In addition to the planets orbiting the sun and asteroids, there's small little dust particles orbiting the sun, and they reflect sunlight, and they change with time, so the zodiacal light's not constant. Sometimes it's bright, sometimes it's not. You just have to remember to look. Excuse me. All right, in your own garden. You've seen this before? Yeah, I'm glad to hear that, Yes. I know from some of you who've showed it to me yourselves this past week, you've got spiders in your garden. What's happening here? Off of each of the strands, light's being reflected to you, and when the difference in the light path from the strand is exactly equal to the wavelength of blue light, then you get the blue piling up, interference, and you get nice bright blue. If it's a bit longer and it's equal to the wavelength of green light, you get the green and red light the same. This is interference. The place where you can see this easily is in something like a CD, a compact disc. You can always see a rainbow in that, and that's because the grooves are all uniform. You get interference. Interference also is what you see in a soap bubble or an oil slick in the road, where the light reflects off the surface, but some of it penetrates and reflects off the back surface, comes back out, and where those pile up at a particular wavelength, you'll then get interference intensity, and you get these colors in a soap bubble. Well, of course, evolution will do anything physics allows, really, and that's where the jewel beetles get their color. That keratin in their carapace is slightly transparent. Some of the light reflects right from the surface. Some penetrates. Only a wavelength or a couple wavelengths of light into the surface reflects from the back. The light comes out, and in some places it's evolved so that it's exactly the distance in the carapace is a multiple of the wavelength of red light. Other places a multiple of the wavelength of green light. And so you can see this sort of color and interference in the natural world. And here in South Africa, there are lots of things like this. Iridescent flies, iridescent beetles, they're quite common, you just have to look. Well, once in a blue moon. Some of these things I've showed you are uncommon, and you may think that you can only see them once in a blue moon, but I hope what you're going to take away from this lecture is that if you look more carefully, you can see them more often, and I hope now you'll see them with more understanding too. Now, that's going to be the end of the first lecture, but I've left time. I want to take questions on this lecture before I start the second one, because I fear that those questions running around in your mind may disappear with what happens next in the next one. So some of you may want to stretch. I don't mind if you move around a bit, but let's try to keep the noise level down while I take some questions. I would rather you didn't leave because we're packed and you're going to have trouble getting back, but some of you may want to leave for some purpose. If you come back after I already start again, then just please do that quietly. So, questions? Yes, ma'am. What is the cause of a ring around the moon? There are two things that can happen to give you a ring around the moon. One of the easiest for you right now is if there's high Cirrus, you get the 22-degree halo, just like the sun. That's one. But sometimes that ring is in much more closely, and you'll see that when there's a lot of water vapor about. And in that case, we're talking about diffraction and scattering again. It's a bit like the glory, but you don't see any color in it. So there are a couple ways you can get rings around the moon. The one to watch for is when there's high Cirrus. You just like with the 22-degree halo for the sun, but because the moon is not so bright, you're much more likely to look up and then you can see the ring around the moon. You technically could get a ring like that around a bright star or a planet, but I think it would be pretty faint and hard to see.
And then you received from Cape Town with the various reflections around the stone.
Yes, from Lawrence. Yeah.
Why was the second ring, its rainbow, not inverted?
Oh, why was the second rainbow not inverted? Wasn't it?
No. It had the same yellow at the bottom as the original.
That's interesting. Okay, I've been asked why for that interference set of rings wasn't the second one inverted, and I'm going to tell you right now, I don't know. Now, it's possible other people do, but glories are not fully understood, and I don't actually have a deep enough answer to glories to answer that. Thank you for the question. I'm not coming back to you for another year at a minimum to tell you what I find out. Lawrence, do you know the answer to that? Speak up very loudly. Yeah, well, that's a good way to go.
You must have seen X-ray diffraction photographs taken when the crystal is spun and its backscatter to produce a set of rings.
Yes, but the question was about the dispersion.
Yeah.
Why?
Yeah, but I suspect if it's a reflected interference effect, you would probably get the same spectrum from each plane that's getting reflected.
Was that edifying?
I didn't understand.
Okay, we're gonna leave that as a lookup for me. Yes, sir, you had a question.
Yes, double rainbows are very common, but do you ever get triple rainbows?
Oh, good question. Double rainbows are common. Do we get triple rainbows or quadruple or quintuple or so on? And the answer is yes, you do, but we humans don't get to see them. The double rainbow, sorry, I didn't answer that. The reason the double rainbow, the color's reversed, is the light bounces twice inside the raindrop, and with the additional reflection, you get a reversal of the colors. For the triple rainbow, it bounces 3 times. For the quadruple rainbow, 4 times. And when the angles get like that, there's a lot of light loss. It's hard to see because it's not very bright, and it's back towards the sun. So the additional rainbows are there, but they're back towards the sun and they're faint, and they're just very hard to see. You can do it in the physics lab. You can measure them with instruments, but we don't see them with our eye. Yeah, so I mean, excellent question. Okay, I have got another lecture to give you folks. If you would like more information on atmospheric optics, this is a website that I recommend. It's called At Optics. It's by a man named Les Cowley. There are other choices, but this one is excellent. And so there's a resource for you. Right, let's go on a very different trip. From the Bay of Fundy to black holes. Some of you were at the movies yesterday, where we were watching tidal bores, and we watched a long, long film slowly watching the tide drop at the Bay of Fundy. These Hopewell rocks right here, I've got kayakers out paddling around. I've never done this, by the way. I am half Canadian, and I've not actually ever been to the Bay of Fundy. It's on my list. In Brittany, I've seen tides nearly 10 meters. You can get big ones elsewhere in the world. Bay of Fundy up to 15 meters. Looks like a good place to go, doesn't it? Let's look at a tide chart. Cape Town tide chart last week. So what are we looking at? This is time, and each of these bands right here are a day. Here's last week, Thursday, Friday, Saturday, Sunday. I took it from last week because I wanted it at full moon, when we've got a very high spring tide. This is the high tide, the low tide, high tide, low tide. And notice that there are 2 tides per day, and it takes a little bit longer than a day to go through 2 tides. 2 tides in just a little bit more than a day. And that as the moon goes through its phases, the range of the tide drops. This is spring tide, this is neap tide. Here in Cape Town, the total tidal range, 1.9 meters. Let's look at the total tidal range at the Bay of Fundy for the same week. It was 1.6 meters. Wait a minute. The tidal range at the Bay of Fundy was less than in Cape Town? And the answer is yes, just outside the bay, in the open sea. And it's the tides in the open sea and for the global Earth that I'm talking to you about today. I'm not going to dwell, except right now, on the problems of how the shape of the land and the bays and the rivers and the currents in the ocean distort tides. I'm interested in the general shape of tides and how they work, not only here on the Earth, but elsewhere in the universe. Here at the Bay of Fundy, in this diagram, here's the northeastern state of the US, Maine. Here's New Brunswick, one of the Maritimes in Canada. Here's the Bay of Fundy. The tidal range right there on that is 3 meters. Just out here, it's 2 meters. And then it goes up and up and up and up and up. And as we're going to see, the combination of the sun and the moon produces a big bulge in the oceans. The Earth turns under that bulge, so from the land, it looks like this mass of water's coming in. And as the mass of water comes into the mouth of this bay, the bay gets shallower and it gets narrower. There's nowhere for the water to go but up. And so it is the geographic squeezing of the bay that pushes the tide so high. That's a geometric effect. The basic tide, nowhere near that kind of range. Are spring tides dangerous? Well, over the Christmas period, you get plenty of people drowning. That's not always the fault of the tide. But indeed, there's from News 24, back in December, watch out for the spring tide. And so here are the questions I want to address. What are tides? Why do they occur? Why are there 2 tides per day? Why are the 2 tides per day different from each other? Let me just go back. I forgot to point that out to you. Look at the tides here. High, low, high, low, high, low. You see the oscillation? The 2 tides, the second one's not as big as the first. If you're a fisherman or a diver, you knew that already. What are spring and neap tides? What are earth tides? There are tides in the earth too. Are there tides on other planets and moons? Why do we see only one side of the moon? Did you know that had to do with tides? Do stars have tides? Do galaxies have tides? And what about those pesky black holes? So you can see that I'm going to connect an awful lot that has to do with tides. Here's a real picture of the Earth and Moon taken by the Galileo mission. The moon's further away, they're actually farther apart, so this is a bit of perspective, but they're right to size. The Earth's darker, the moon is darker than the Earth, and the moon's much smaller than the Earth. The moon dominates tides on the Earth, the sun affects tides on the Earth. Now, since the tides come from gravity, why should the moon matter more? The gravity of the sun's vastly greater. There's a reason why we orbit the sun, not just the moon. And the answer is that the tide is not caused just by the gravity. It's caused by the difference in the gravity from one side of the Earth to the other. And that's the concept we need to look at. So I made a graph. This is the strength of the moon's gravity. I calculated that, and just in a spreadsheet, calculated the strength of the moon's gravity dropping off as you move away from the moon out to the distance of the Earth. Even close in, that number right there says 0.012. The gravity that's holding you down right now on that scale is 10. And then as we move far away from the moon, the gravity drops from this tiny, tiny number. Remember, 10 in these units is holding you to your seat. This tiny, tiny number, but with the moon over here, the gravity's stronger on the near side, and it drops and it's weaker on the other side. The sun's gravity's stronger, but because it's so far away, the change in the sun's gravity across the Earth is less. So the moon actually has 2.2 times more effect on the tides than the sun does, but they both matter. The concept we have to understand the tides is a concept that you were taught at school wasn't true. And I have to tell you now, it is true. We need the concept of centrifugal force. When you were taught science at school, probably the teacher said there's no such thing as centrifugal force. Like you can hear them chanting it. And in what we call an inertial frame, if we're in space and we're not moving, just watching somewhere else, that's true. And so when you go around a corner in your car and you feel yourself being flung out in the car, what's really happening, the car is turning, your body's trying to go straight, and the car has to push on you to make you go that way too. But within the car, if we're not looking out, we sure feel a force pushing us. If we're on this fairground ride right here and we're not looking outside, why don't we fall down due to gravity? And the reason is because of the spin, the centrifugal force is balancing the gravity, keeping you pinned up there. In a rotating reference frame, centrifugal force is a real force in physics in that accelerating, rotating reference frame. And that's what the Earth-Moon system is. So here's the Earth, and here's the Moon, and they're now fixed. I've done away with the orbit. We're now rotating with them, so we don't see them move. If that were really happening, they would fall into each other because of gravity. But in this reference frame, they don't fall into each other. Here's the strength of the moon's gravity. There it is on the center of the Earth. It's stronger on this side, so the arrow's longer. It's weaker on that side, the arrow's a bit shorter. And of course, up the top, it pulls too. And so what I did is I put in there the centrifugal force arrows. To keep the Earth and the moon fixed, the centrifugal force has to exactly balance the gravity here at the center of the Earth. Now, the moon does actually raise tides in the ground. When the moon passes high overhead here, the ground stretches up by about 10 centimeters. But ground's not very compressible, so the tides on the Earth are small, but there are Earth tides. We can measure those. The water, on the other hand, can flow. And the gravity of the moon produces this change in the gravitational field of the Earth, and the water flows in there, and you get a bulge. But if you think it's just because the moon's pulling, then you'd expect a bulge over here. Why do you get a bulge over there too? What causes the one on the other side? Here's the answer. The centrifugal force balances here at the center of the Earth. That force vector I've now put on the stronger gravity of the moon here, and there's a little bit left over. And so the water flows down here because the moon's pulling. Over here, the centrifugal force vector is bigger than the gravity of the moon. There's a little bit of centrifugal force left over, and the water gets flung out. And so you get two bulges for the tide. Tides are a stretching force. There's another mantra to take away. A tide is a stretching force. Tides stretch things. And boy, when we get to the black holes, are we going to see that? So up here, the sun and the moon are in the same direction at new moon or opposite directions at full moon. No matter, there's a bulge of the moon's gravity tugging one way, the centrifugal force pushing the other way, caused by the moon, and there's another one caused by the sun. The moon's one is bigger, but when the sun and the moon are along a line, the sun and the moon's tidal bulges pile up on top of each other, and that's when we get spring tide. Spring tide comes at new moon and full moon. A week later, or a week before, when the moon is at 90 degrees to the sun, the moon's bulge is towards the moon, the sun's bulge is towards the sun. They're not piling up, and so the highs are not as high and the lows are not as low. That's the cause of the spring tides. But now, why do the tides not come twice per day? There's the bulge. The Earth turns once, and you don't get back to high tide because the moon moves. I've greatly exaggerated it here. Here's the Earth, and I've drawn a squashed out Earth. There's the moon. It's got a tidal bulge. And the Earth rotates once. You're on the Earth, this little arrow. You come around again thinking you're coming back to high tide, but by then, the moon's moved over there. And you've got to keep rotating a bit further before you get back to the bulge. The moon's dragging that bulge forward. And the calculation is fairly easy. The length of the month for the moon to go through its phases is 29.5 days. We've got 24 hours. And so every day the tides advance on average by 50 minutes. Now you go home and look at your tide tables for Cape Town and come back and tell me if you saw me tomorrow, oh no, it wasn't 50 minutes, it was an hour and 12. That's the Benguela current and the Mozambique current and the shape of the Cape Peninsula and all the things that perturb the tides if you're close to land. On average, that's the change day by day. Remarkably, tides are not well described on the internet and in many books. And so I had to call in the resources of an artist to do this drawing, and he's not very good, as he is me, but it makes the point that I would like to make. So not to scale. The moon's orbit is tilted to the Earth's rotation axis. I've exaggerated it. I put the moon over here, and so here's the tidal bulge towards the moon. There's the centrifugal one on the other side, and here we are in Cape Town, and there's high tide. You can see how high the tide is. We rotate around to the other side of the Earth, and now here comes the second high tide of the day, but look, we're nowhere near the bulge, and that high tide's smaller. So it depends on your latitude. The reason why the tides alternate, high tide, lower high tide, bigger high tide, lower high tide, is that as you go around, you're passing through different parts of the bulge, depending on where you live on the Earth. That's what causes the difference in the two heights of the two tides in a day. Now, this is a very important point, and it's got lots of great applications. I put the moon on the other side. I'm sorry. I hope I'm not making you dizzy. Here's the tidal bulge again with my drawing. And because the Earth spins roughly 24 hours, and water's got viscosity, the water can't flow fast enough to keep the bulge pointed exactly at the moon. The Earth's rotation drags it forward a little bit. It's in equilibrium, but the direction to the bulge is slightly in advance to the direction of the moon. Greatly exaggerated here, but slightly in advance. The gravity of the moon is then latching onto that bulge. It's pulling on it, and there's a net pull that is in the opposite direction to the Earth's rotation. Over on the other side, there's a net pull in the direction of the Earth's rotation, but it's weaker over here because the gravity's less strong. And so what's happening here is the moon is tugging on the Earth as it tries to rotate, and it is slowing the Earth down. If you were here 600 million years ago, just before the Cambrian explosion, when life came out onto the land, the day was 22 hours long. If you were here 300 million years ago, out in the Karoo, where we've got some nice fossils, the day was 23 hours long. Day's now 24 hours long. It's getting longer. It is really slowing down. It slows down by 1.7 milliseconds every century. Probably not going to affect your watch, but we astronomers can measure that easily. Now, spin, the rotation of the Earth, angular momentum is a conserved quantity. You can't get rid of it. And so as the Earth slows down, that spin has to go somewhere. And this bulge on the Earth's tugging on the moon in the direction it's going, and that's causing the moon to drift away from the Earth. And the moon's drifting away from the Earth. This may disturb you to hear this, but it's going away at 4 centimeters every year. It's getting smaller. Does that matter? Actually, yes, it does. How do I know that? How can I throw out such infinitesimal numbers for something 384,000 kilometers away, and I can tell you next year it'll be 4 centimeters farther away? Here's the experiment. The astronauts left these nice retroreflectors on the moon, little box of mirrors, and if you shine a laser on the moon, it bounces in there and it comes back to you. And when I worked at the University of Texas when I was a graduate student, we had a laser that was shot out of the 2.7 meter telescope. Every night the moon was available, was fired at the moon. The laser had a power of 1 billion watts. It was illegal for planes to fly over the observatory because the Federal Aviation Administration realized that if a pilot looked down at a 1 billion watt laser, you'd have a blind pilot, and that's not a good idea. And so we didn't have any planes. The laser beams fired out at the moon, the light traveling almost completely in a vacuum, but not quite. You've got to correct for the fact it's moving slower in the air, hits the moon, bounces off the mirror, comes back to the telescope, and all you do is time it. 2.5 seconds approximately, and it tells you how far away the moon is. It also tells you where you are on the Earth. And as the continents drift, and as Africa and South America spread at 4 centimeters per year, you can measure that. That's not, continental drift is not some theoretical concept. We measure the continents floating around with these experiments. We measure the rotation of the Earth to incredibly high precision. We can see the El Nino coming. Every few years when the El Nino comes in the Pacific and the ocean currents flow up against South America, as they flow to the east, the Earth slows down, the day gets a millisecond longer, and we can measure that very easily. So the Earth and the moon are interacting. Now, I gave you a website to go to for information on this for the last talk. For this talk, I'm going to give you a different piece of homework. If you would like to follow up on this, there's a really nice place where you can go to get full information. It's called Hermanus. And if you stand there at the main viewing platform and turn your back next September on the whales and look at what's there, some astronomers did, I don't know who did this, but it's good. The physics is correct, the drawings are good, there's information on eclipses too. So next time you go for a walk out at Hermanus, read the signs and remember this lecture. Eclipses of the sun occur when the moon passes directly in front of the sun and blocks out the photosphere, the bright part of the sun, and then you can see the very faint 2 million degree corona. We had some films on that yesterday. You cannot in your life ever experience a total eclipse without being at it. No film, no picture, nothing can come to the real experience. One reason is your eye has got tremendous dynamic range, and we haven't got any equipment with the dynamic range of the human eye. And there's a whole ambiance to an eclipse that you just can't get unless you go. Well, why don't you come with me in August? August 21st, we've got a total eclipse of the sun in the US, and for the 5 days before that, there'll be a group of people going with me down the Salmon River through Idaho. It's a small river. The biggest waves are about 4 meters, so it's not serious water. And we'll do some river rafting, watch a total eclipse. These total eclipses only occur when the moon passes in front of the sun. Now, remember the supermoon? The moon's in an elliptical orbit. It orbits farther at some times and closer at other times. Interestingly, the man who actually proved that was true and that Kepler's laws of motion is true was a teenager by the name of Jeremiah Horrocks, and you might have noticed that the name of my institute is the Jeremiah Horrocks Institute. He was an absolute genius. He did brilliant work, and he died when he was 22. Yeah, I figured that, anyhow, he worked about 8 miles, about 12 kilometers down the road from my office, so we named our institute after him. If the moon passes in front of the sun when it's out at perigee, it can't quite cover the sun. You get what's called an annular eclipse, or a ring of fire. The moon's drifting away from the Earth. Now, some years ago, friends John and Sandy Folks were with me for that. We were on a Rovos rail trip to Zambia for a total eclipse of the sun, 2001. And I was lecturing to the people on the train, and these people were eclipse chasers. If you go, you'll understand that. It can be addictive. But they're like twitchers. One of them says, oh, how many have you seen? So we've seen 7 eclipses. Oh, yeah, well, we've seen 11. We've seen 14. The Goodmans had seen 23. Now, before I carry on with this, Goodmans, are you here? Oh, good. The Goodmans had seen 23, and in my lecture I pointed out that because the moon's going away from the Earth at 4 centimeters per year, these total eclipses are not forever. In 600 million years, the moon will never be able to cover the sun. And somebody from the back of the audience, I said, the eclipses will only last for 600 million more years, and somebody shouted out, and the Goodmans will have seen every one. The near side of the moon. Oh, and this picture is quite cute. This is a real picture, multiple exposure, of the International Space Station crossing in front of the moon. We watched a couple crossings last week. I hope some of you did too. The space station's often visible here in Cape Town. Absolutely brilliant for a few minutes. There's the near side of the moon. It's the only side we ever see. There's the sun, there's the Earth. And as the moon orbits the Earth, it's rotating at the same velocity that it's orbiting. And so it is rotating, but it rotates at just the same rate that it orbits, so it always keeps one face towards the Earth. The other side looks very different. Why is that? The answer is tides. The moon was formed first out of a collision of a big body with the Earth, and then later lots of things crashed into the moon and made these gigantic craters, things we call the seas, Mare Crisium, Tranquillitatis, Fecunditatis, Serenitatis. Sea of Tranquility, you remember when the Eagle has landed? Some of you don't remember the first landing. I'm glad to see that that's true in this audience. Those big impacts left the remains of huge asteroids underneath the surface, and the crust on the other side of the moon is about 60 kilometers thick. It's very thin on this side, and they're lumps. And the gravity of the Earth locked onto those lumps and slowed down the moon's rotation until the moon got locked to the Earth. It's called tidal locking. The moon is currently doing tidal locking to the Earth, and one day the Earth will be tidally locked to the moon. At that point, the length of the day and the length of the month will both be equal, about 47 days. But there'll be no life left on the Earth, and I'll mention that again in a moment. It's very far in the future, and the sun will be gone too. Off to Jupiter. This is a real picture, not photoshopped, from the Galileo mission. There's the giant planet Jupiter, gaseous atmosphere. Its great red spot, which is a hurricane the size of the Earth that's been blowing for at least 300 years. And the two moons, Io and Europa. Io and Europa are both about the size of the Earth's moon, but boy, are they different. Now, before I show you, you saw Io in the last talk. We'll look again. Io is covered in volcanoes, and it's in an elliptical orbit. Jupiter is causing a land tide in Io that is really stretching the moon seriously. Jupiter's big, and Io's close to Jupiter, and the tide stretches Io more when it's closer and less when it's further. And also, because of the elliptical orbit, Io speeds up when it's close and then it slows down when it's further, according to Kepler's laws. And so it seems to wobble back and forth towards Jupiter. And what Jupiter's doing is it's stretching the land on Io. And the friction from that, just like rubbing your hands together, in this case is enough that the inside of the moon has melted and it's covered in volcanoes. So the volcanoes on that moon, and it is completely covered. Here's a flyby when the satellite actually caught an erupting volcano blasting stuff out into space. All of that's caused by tides. Much more interestingly is Europa. Europa is the next moon out from Jupiter. The tides are a bit smaller, but they still exist, and they've caused Europa to heat, but not to have volcanoes, at least not erupting volcanoes. Europa is completely covered with a thick layer of ice, probably 4 kilometers thick, maybe as much as 25. And underneath that is an ocean. We can tell that from various measurements. Europa has got a water ocean covered in thick ice. The tides from Jupiter crack the ice. You can see all these great cracks, and the water from the ocean wells up and then stains the surface with contaminants. There's something in that ocean. There's another little moon that orbits Saturn called Enceladus. It's much smaller. It's only 500 kilometers across. We don't know what heats it, but it's got a hot interior, and it's cracked here. These are called the tiger stripes by the people who discovered them. And we saw with the Cassini mission seawater, salt water. We can tell that spectroscopically. Salt water is getting blasted out of those stripes. Enceladus has got a saltwater ocean. Europa probably has a saltwater ocean. Now, here on the Earth, some people think that this is where life first evolved. 4 kilometers underneath the ocean, no sunlight, but heat from volcanoes is superheating water, which blasts out of the volcano, the geyser, Let me get that to go again. And bacteria can live off of the minerals, and then crabs and fish and other things can live off of the bacteria, and you get this ecosystem that doesn't need sunlight. Maybe on Europa and maybe on Enceladus. And as soon as we, astronomical community, not me personally, can talk a funding agency into providing the $3 billion it'll cost, we want to send a satellite to one of those little moons with a little nuclear reactor on it so it's hot, and it'll land on the ice, and the heat will melt the ice, and it'll just sink through the water until it pops out in the ocean, and then a little swimmer will go around and look for something like this, maybe life on another planet. It's coming. We might get there. Right, here's another concept, the Roche limit. Roche is named after an astronomer physicist of the 19th century, Edouard Roche, and he calculated how much gravity you need and under what circumstances the tides would be so great that a body couldn't stay together. And that's what's happened to Saturn. If you took the Earth's moon to where the rings of Saturn are, the tides stretching the moon would be stronger than the gravity of the moon, and they would be stronger than the molecular forces that hold the rocks together, and the planet would tear the moon apart into little pieces. And that's what happened on Saturn. Something got torn apart to form these rings, which are just millions, billions, pick some large number, of small icy rocks, size of my head, size of this room, little bits of dust. Here's an artist's impression of the rings of Saturn. The rings are 137,000 kilometers away from the planet to start with, and then more, but they're only 100 meters thick. All these individual moons. This is what happens if you get too close and the tides tear you apart. I'm going to give you a warning about a place I don't want you to go later, because this could happen to you. Farther out in the solar system, the planet Uranus. This is a real picture, not photoshopped. This was taken by the Voyager mission, 1989, as it whizzed by Uranus. It took this lovely picture of Uranus. Now, we could never see this from the Earth. Uranus is so far from the sun, you only ever see it fully lit. It's always almost full. Here you can see it as this lovely crescent, and there's its little moon Triton, right there. Triton's smaller than the Earth's moon. Triton has a diameter of 1,200 kilometers. The moon is 3,400. So it's a little moon that orbits Neptune, and Neptune's a big gas planet, but Triton probably got captured from farther out. It's a body very much like Pluto that was captured in Neptune's gravity. Here's Triton as it looks with a close-up from the mission. It's a wonderful little moon. It's the coldest place we've ever been until we got to Pluto last year. Pluto's not very different. On one side down here where the sun's shining, it's summertime. And summertime on Triton, it warms up to a balmy minus 235 Celsius. And with that, the nitrogen ice evaporates and blows out as geysers, and there's an atmosphere and the wind blows, and you can see the streaks from the contaminants of the nitrogen blowing in the wind. And it blows around to the winter side where the temperature is minus 238. And at minus 238, the air freezes and falls to the ground as snow. Now, it takes 160 years for this thing to go through a full orbit of the sun. And so if you come back 40 years from now, for those of you who can come back, this bit up here will have the geysers, and that bit down there will turn like the top bit as the seasons change. But Triton orbits about Neptune the wrong way. Almost everything in the solar system orbits the sun in the same direction. It was the spin of the original solar disk. And the moons tend to go around in the same direction. But in Triton's case, it got captured by Neptune. Neptune's spinning this way with only 16 hours. The moon raises a tiny tide, just like here on the Earth, and the spin drags the tide forward. And so the moon is tugging back on Triton, and the day on Triton's getting longer, just like the day on the Earth's getting longer. But the push of Neptune on the moon is pushing that way, but the moon's coming this way, and so the moon's orbit's shrinking, not getting bigger. If you can come back in 2 billion years, for those of you who believe, the people who've claimed that the first person who's never going to die has been born, I think that that's absolutely crazy, but the statement gets made. 2 billion years from now, that moon will come within the Roche limit. It's going to be shattered, and Neptune will have a ring that far, far exceeds the ring around Saturn. It'll be really beautiful if anything gets to see it. Maybe nothing will see it. When the Earth was born 4.65 billion years ago, the sun was 30% fainter than it is now. Its radius was about 30% smaller. and there was a lot less light getting to the Earth. And yet we know from the fossil record, fossil stromatolites off of Australia, from 3.5 billion years ago, we had tropical oceans with a temperature of 30 degrees Celsius. And yet the sun was much fainter. Why is it that the Earth has remained fairly constant in temperature for 4 billion years? That's absolutely critical to the fact that we exist. Why did it do that? The initial atmosphere of the Earth was almost all carbon dioxide. That's still true of Venus. It's still true of Mars. That carbon dioxide is a potent greenhouse gas. You've been reading about that with global climate change. We have pumped the carbon dioxide in the atmosphere of the Earth up dramatically in my lifetime, yours too, for most of you. And that increased carbon dioxide blocks infrared radiation from the ground, and it's changing the global climate. Well, way back then, this thick carbon dioxide trapped the heat on the ground when the sun was much fainter. And back then, that was a good thing because the planet was warm. And as the sun got brighter and more heat was getting to the ground from the sun, the carbon dioxide was dissolving into the ocean, turning into limestone, and the carbon dioxide dropped at such a rate that the planet managed to maintain a fairly constant temperature with some variations like ice ages for 4 billion years, which is what has allowed such complex life as us to evolve here on this planet. We don't know if that's a coincidence. James Lovelock, with his Gaia hypothesis, suggests that there's actually a positive feedback mechanism and the life has caused that to happen. Others don't know. In that question, that really big question, are we alone? Are we the only life in the universe? Are we the only intelligent beings? The probability of life on other planets is much greater if this feedback is actually guaranteed than if it's a coincidence and therefore much less common. We don't know the answer to that. So the sun is growing bigger, and it will cause the oceans to evaporate and this planet to become unlivable for creatures like us in about 1 to 2 billion years. Nobody's going to see that moon of Neptune shatter into a ring. Bacteria living under the ground, like in the gold mines up on the Witwatersrand, those bacteria may survive into the much farther future, living off the interior heat of the Earth. But big creatures on the surface, we've got 1 to 2 billion years and it's over. You think, all right, let's go to Mars for a little while. But when the sun gets to its very brightest, it'll be 6 times brighter out at Pluto than it is here. It's going to vaporize Pluto too. Go to the stars? Probably not. They're a long way away. That may not be doable. All right, tides, we're continuing. Here's a nice picture by the astronomy artist Mark Garlick of what we call a cataclysmic variable. And there is, the top people in the entire world who study these stars are right here at UCT. Brian Warder wrote the textbook decades ago, Patrick Vogt. These stars are stars that are intensely studied here by astronomers in Cape Town. These are binary stars where there are 2 stars orbiting each other. One of them has already lived its life. It's grown to be a red giant. It's blown off its outer atmosphere, and the core has collapsed to be what we call a white dwarf. That's the remnant of a star that no longer can make energy. It's got the mass of the sun, or 6/10 the mass of the sun, but it's only the size of the Earth. And its companion star, which is a bit smaller, evolves later. And in this situation, the companion star is now swelling up. And thanks to Edward Roche again, there's a lobe called the Roche lobe, which is where the gravity is equal over the star. The gravity of this white dwarf buried down here at that point wins, and as the star swells up, the gas falls down onto that star. But they're orbiting each other. And so as the gas falls, the stars move to the side, and you end up with a disk of material around the white dwarf. As the material falls onto it, it slams into the disk to produce what's called the hot spot. And these things are great fun to watch at the telescope. They flicker, they get brighter and dimmer on a time scale of seconds. And then over years and decades, some of that material, mostly hydrogen, rains down onto the white dwarf. And when enough hydrogen builds up on the surface of the white dwarf, finally there's enough nuclear fusion is started and a gigantic hydrogen bomb the size of the star goes off and the star blows up as a nova. And it gets 10,000 times brighter for a few days and it blows away all the extra stuff and then more starts falling down onto it. It can do that every century or so. They're called novae. This is tide. This is tidal stretching that produces that shape, and it's the common fate of binary stars across the universe as they get old. Now, binary stars, here's one of my favorites. These are the heartbeat stars. Let's first put the graph in perspective. This axis right here is time in days, and this is a funny astronomy way of counting days, but this is 180 days from left to right. The brightness change here is about 1% from top to bottom, and we discovered this with the Kepler mission 5 years ago. We noticed that the star was going blip, 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 blip every 42 days. This is only 180 days. We've got 4 years. It keeps doing this. And it looked a bit like an electrocardiogram, so we called it, and the nearly 200 others like it, heartbeat stars. They went into a box we call the WTF box to start with. That means, what the flip is that? I don't know when I first looked at it. Boy, if you want to see a happy scientist, you want to see a happy astronomer, show one of us something that we don't know what it is, and we're in kids' heaven. My goodness, this is fun. Let's figure it out. Well, I had a student named Kelly Hamilton who got her PhD last month. And she took introductory astronomy from me about 8 years ago. And 8 years ago, we didn't even know these existed. And for her PhD, she wrote the definitive study of this new class of stars that we didn't even know existed when she was an undergraduate. The opportunities are just amazing. Blip, it's not only going blip, 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 but when you fold the light curve so that all the blips pile up on top of each other, like down here, it's also wiggling, and all the wiggles always pile up in the same point. Well, that was a clue. A group of us figured this whole thing out. And here's an animation from my colleague, Jim Fuller. Jim got his PhD about 3 years ago at Cornell University in New York State, and he was then offered the most prestigious prime postdoc on the planet. He was given a postdoc at Caltech, often rated the top university on the planet, simultaneously with a postdoc at the Kavli Institute of Theoretical Astrophysics. The guy's just brilliant, and he's made us a nice animation. These two stars turn out not to be so special. They're a binary star, but they're a binary star in a really eccentric orbit. This is like Halley's Comet orbiting the sun. It's a long eccentric orbit, and the stars move slowly, and then they come close together, and they whip around, and at the close point, they almost touch. And the tides just go haywire all over the place. We've had the theory of that for 50 years. We call it tidal excitation of oscillations, tidal variation in the orbit, tidal interaction. It affects the inside of the star. For the first time, we were able actually to see it. And so these stars in this very eccentric orbit, here they come, they whip around each other. That's where the little spike comes. And that point, it stretches the stars out of shape and sets them to wobbling. And those wobbles, now we're in my field, astroseismology. Now we can look inside the star and learn lots from it. And so there's an artist's impression of how those stars get stretched out at periastron. This is a NASA press release from just a few months ago. Another postdoc at Caltech, Avi Sporer, and a group of us, I'm co-author on that, produced another paper on these heartbeat stars. They have lots of implications throughout stellar astronomy. But the exciting thing is tides did it, and we didn't even know they existed until just a couple of years ago. Well, let's go out even further in the universe. Oh my goodness. What is that thing? This is a very deep picture of the universe taken with the Hubble Space Telescope. And we are looking out far, far, far into the depths of space. Let me remind you that you cannot see anything as it's happening now. As I stand here talking to you, those of you in the back of the room, you're about 10 meters away from me. Light travels 300 million meters in a second. If you're 10 meters away, you see me as I look a 30 millionth of a second in the past. I don't do anything a 30 millionth of a second. You can't perceive a time so short. But as soon as you look out to the sun, you see the sun as it looked 8 minutes ago. You look out to Alpha Centauri, you see Alpha Centauri as it looked 4.3 years ago. You look out to this galaxy and you're looking out tens of millions of light years into space. And for this particular picture, there are loads of galaxies. Here's another one, here's another one, and another one, and another one. Each one of these contains about 100 billion stars. That galaxy is 100,000 light years across. It takes 100,000 years for light to cross that galaxy at the speed of light. And we're looking back 60 million years into the past. For the faintest smudges in this picture, you're looking back almost to the beginning of time. You're looking back at the faintest things to the time of the formation of the first stars. With the James Webb Space Telescope to be launched next year, we claim we're going to see the first stars, and there will be nothing beyond that. If there are things beyond that, we're going to need a new model of the universe. This Big Bang model of cosmology is going to be seriously tested next year with new observations of the very first stars, which we'll see with James Webb. In the case of this galaxy, 100,000 light years across, full of young stars just been born, shining with bright blue light, scattering off of dust like in the Pleiades, or old yellow stars down in the center, old stars like the sun. Another small galaxy passed by fairly recently, probably a couple 100 million years ago. And when it passed by, the tide stretched the big galaxy, and the stretching whipped out stars by their millions. And so this is a tidal tale where the tide of the passing galaxy whipped these stars and flung them out like the bulge in the Earth's ocean. It didn't hurt the stars in any way whatsoever. These stars are far apart. Earlier, I shrank the sun down to the size of my head, and the Earth was about a millimeter in size at the back of the room. Alpha Centauri, the closest star, is the size of your head. But on that scale, if my head's the sun and your head's on the right scale, it needs to be in Nairobi. It's a long way between the stars. And so when a galaxy passes by and stars get flung about, even when galaxies collide, the stars don't collide with each other mostly in the outer parts. And so these stars got flung out, their planets got taken with them. I am so envious. This would be such an amazing place to be an astronomer, where you would get this look down into the heart of the galaxy. Well, let's look into the heart of a galaxy. This is another giant spiral galaxy. 100 billion, 400 billion stars, all orbiting about a common center. The galaxy is full of dust, that dust that produces the blue light around the Pleiades, that scatters the light that we saw in the first talk, that produces the blue of the sky. The galaxy is full of dust, and you can see the blue over here. On this side, it's blocking the light from behind. And so when you go out and look at the Milky Way on a dark night here, and you see those dark bands running through the Milky Way, those dark bands are the dust between the stars absorbing the starlight. There's not much dust out there, but it's the only thing that absorbs light. The gas lets the light come through. And down in the middle of the galaxy, there is a monster. When stars evolve, in the case of the sun, it will grow to be a red giant. We know that, we can calculate it, but with 100 billion stars in the galaxy, we've seen lots of stars that have already done that. The sun will die as a white dwarf, and 97% of all stars end up as white dwarfs. They simply collapse till they're very dense, about a ton per cubic centimeter, spheres of carbon and oxygen with a little bit of hydrogen and helium. They're about the size of the Earth, and they're usually about 6/10 the mass of the sun. For very, very massive stars, much, much bigger than our sun, when they evolve, they build up an iron core. And that iron core, iron is the most tightly bound nucleus of any atom. The star can no longer make energy when it gets an iron core, and it eventually has what we call the iron catastrophe. The core heats to about 1 billion degrees, and all of a sudden there is so much energy that the light can tear the iron apart and turn it back into helium, and that soaks up all the energy. The core catastrophically cools. It can no longer support the surrounding star, and the core of the star in 1/1,000,000th of a second goes whoomp and collapses. During that 1/1,000,000th of a second, it pumps out more energy than the rest of the visible universe. And that energy blasts the star to bits as a supernova. Explodes, and it blows stuff out into space. That's a good thing, because those oldest stars we can see are made of only hydrogen and helium, and it's those supernovae blasting material out into space that produce the carbon, the nitrogen, the oxygen, the things that make up our bodies. Your stardust. If you're wearing a gold ring like I am, that came out of a supernova explosion. That's the only time the universe can produce this stuff, is during one of those explosions. And in the core, frequently what happens is the collapsing core, the gravity gets so strong, even light can't escape, and a black hole is left behind. For a black hole, the object is still there. It usually has a mass to start with of just a couple times the mass of the sun. A black hole with twice the mass of the sun has got a radius of 6 kilometers, smaller than Cape Town. The gravity is so strong, even at the speed of light, light can't escape, and so that black hole is effectively permanent. But my goodness, does it have tides? You come close to a black hole like that, you come inside the Roche limit, And so down deep in the heart of this galaxy, over its lifetime, a few stars have exploded and produced these stellar-sized black holes. And we can see those in our own galaxy. We can detect that there are invisible things orbiting about other stars, tugging them about. And those invisible things are too big to be anything but a black hole. The evidence for them is very strong. Down here in the center of the galaxy, that black hole, that stellar-sized black hole down there, the stellar density is much, much higher. And the stars are much closer, and a star comes near the black hole, it doesn't get sucked in. Black holes just have regular gravity, it's just strong. But as the star comes by, the tide from the black hole stretches the star and tears it apart. And some of that gas then goes into a disk that orbits about the black hole, some of it escapes. And as that disk orbits about the black hole, it swirls around in this artist's impression, and it orbits the black hole, which is black, you can't see that. And as the material falls in, it releases stupendous amounts of energy before it falls in. Once the material falls in, it can't come back out again. But before it falls in, it produces amazing amounts of energy. It heats the gas near the black hole so hot that 2 tornadoes shoot out of the black hole in opposite directions at more than 90% the speed of light. This is commonly seen, and in these big galaxies, the black holes can have masses of up to 2 billion times the mass of our sun. In our own galaxy, there's a black hole in the center that has 5 million times the mass of the sun. A 2 billion solar mass black hole, it's about the size of the solar system. They're not very big, but my goodness, can they produce some pyrotechnics. And there's a real picture. This is for real, folks. This is made with a radio telescope. You can't see this in visible light, but that thing right there is a galaxy, 100 billion stars. And down in the middle of it is one of these giant black holes, 2 billion solar masses. How do we know it's so big? The same laws of motion for the Earth orbiting the sun, the stars orbiting that black hole have to obey, and we can measure the speed of the stars. And they're going around so fast, the thing they're going around has got 2 billion times the mass of the sun. It's easy to measure, but it's invisible. The only thing it can be is a giant black hole. That disk of material is now shooting out jets of gas over 300,000 light years of space at 90% the speed of light. And this picture is taken with radio waves. You can't see it in visible light, so it's artificially colored red. This one's in the constellation Hercules in the northern hemisphere. It's called Hercules A. There are many others of these. And the telescope that's discovering these in large numbers right now and is really going to pump them out. I saw some brand new ones I'd never seen before 2 days ago when I was down chatting to the chief scientist at SKA, the Square Kilometer Array. Meerkat, the prototype for the Square Kilometer Array up near Carnarvon, with its headquarters here in Cape Town, discover these in huge numbers. This is what one of the things a radio telescope can do. If you're not fully aware of the SKA, it's an international project for which South Africa won the right to place the main part of it here. The first part of it, which should be completed by April of next year, and the extension of that will cost on the order of 1 billion euros. Where's the 1 billion euros go? There are 335 people sitting in an office next to Vincent Pallotti right now working on that. It's full of engineers and programmers and astronomers, people building this international telescope of ultimate importance to the whole planet, hosted right here in South Africa. It's fantastic. So we get these giant black holes. Now, what would happen if you visited a black hole? What does a black hole look like inside? You must wonder that. Haven't you sat around wondering about what it's like to visit a black hole? Well, if you went to visit a black hole with the mass of the sun, a stellar-sized black hole, long before you got near it, as you get near a stellar-sized black hole, the difference in the gravity at your feet and your head, the stretching force, would get up to about 500 million times stronger than the gravity that's holding you to the ground right here. And it's a stretching force, and so you get stretched, and we call that stretching spaghettification. Now, that is not a good Scrabble word. It's a bit long, but you can add it to your vocabulary. So you get stretched as you come in. And if you got near a stellar-sized black hole, you'd be torn not only your component atoms, but the electrons would get pulled out too. You're going to die. But if you go near a 2 billion solar mass black hole, the tides are not so bad. You can fall into a 2 billion solar mass black hole, and if there isn't all this radiation around it from a disk, if it's cleaned everything out, you could fall in and nothing would happen to you. From us watching from the outside, it would look like you just slowed down ever more and never quite passed through because your clock would slow down. And as you passed into the black hole, we would see your clock stop. But you wouldn't. You'd pass right through to the inside. What would it look like inside the black hole? I made a painting of it, but I took it out of the slideshow because it was just speculative. The painting was black. We don't know what the inside of a black hole looks like, and this may disturb you. We are never going to know. It is not knowable. We know the mass is there, but because light can't get out, no information can get out, and there is no knowing ever what's inside a black hole and what it looks like in there. And with that incredibly optimistic hinting, we've done our tides from simple Earth tides as you know them here on the Earth, all the way out to these black holes, and I hope that you will now see tides in quite a different light as you watch them ebb and flow here in Cape Town. Thanks for your attention this afternoon, folks. Thank you. Well, I'm going to take questions, but I don't want anybody to feel trapped. We've had 2 hours already, and you may have other things to do. So at any time you feel like you'd like to leave during the questions, please just do that quietly. I won't be offended. I understand people have other things to do, but I'm happy to take questions then for some time now, so long as none of you feels trapped. So let's go with the questions. Be brave. Once you start, somebody else will go. Back to the first talk. Yes, sir.
I have a two-part question. One, is the distance that the moon is leaving us increasing potentially to 4 centimeters from here?
Go ahead in your second question. I'll repeat it.
And at what stage will it leave us? And secondly, why does the black hole not become a supernova?
Okay, the first question is the speed with which the moon's moving away, is that changing? And the answer is yes, it is changing. I don't know that from measurement because we've been measuring too short a time. But as the Earth rotates more slowly and the moon moves farther away, that effect of the moon drifting away will decrease and it will creep away more slowly. And so the speed it's going away has to slow down. We will never lose it because one day the Earth will have its one face locked to the moon. And at that point, the entire process of drifting away stops and everything becomes stable. Your second question was, why doesn't a black hole become a supernova? The black hole came from a supernova. It was a supernova that exploded that produced the black hole. And once everything's in a black hole, it can't get out. The black hole can't actually blast things out. So it is the remnant of a supernova, but it itself can never after blast stuff out of it. Now, all right, since you're not piling questions on me, Stephen Hawking's theory, if we're to believe his Hawking radiation, suggests that very, very slowly black holes can evaporate. The way they do that is very esoteric. The idea in particle physics is that at all times out of the vacuum of space there's a background energy, and in that energy, the energy of the gravitational field in a black hole, particles come into existence and disappear. So an electron and a positron pop out of the energy field, they gobble up the energy, and all of a sudden you've got these two particles, positron and electron. They then run into each other, they annihilate, the energy comes back. But if that happens near the surface of the black hole, electrons are not just little particles, they're probability distributions, and when you think they're there, they might be there, and they don't know where they are either. That really happens. It happens in fusion in the sun, we can see it. And so occasionally, according to Hawking, when these two particles are created near the surface of the black hole, they're inside, but one of them all of a sudden discovers it's outside by what we call quantum mechanical tunneling, and it can then disappear off into space. And with that as a calculation, a black hole the size of the sun can evaporate in only a gazillion years. But ultimately, the black holes into the far, far future, when all stars are gone, they could evaporate and disappear too. Yes, ma'am. Going back to the... Oh, good question. What if you're off on the wild coast and it's the sardine run and the gannets are raining out of the sky after the fish? How do they counteract the refraction? Well, if they're diving straight down, there's no problem. If they're diving at an angle, they better know about the refraction or there's no gannet left when it starves to death. And so I'm winging this right now. I'm guessing at the answer. Those gannets know how to accommodate for refraction or they would starve to death. They know how to do that. Mostly they're diving straight down. The refraction, they don't go in at an angle, but there will be some refraction, and I'm sure they know how to compensate for that. Say that again? What about fish eagles? No, fish eagle normally will take a fish that's so close to the surface that it just snatches it off the surface. The fish eagle must, I guess if the fish is slightly below the surface, the fish eagle's got to compensate for that too. I would argue, I'm making this up, I would argue that the animals who have to compensate for refraction know how to do that or they wouldn't be with us. I'm just making that up, but I think it's probably true. John? Well, all right, what John said is humans can do it too. So humans are as smart as a fish eagle. Let me reword that. Some humans are as smart as a fish eagle. Yes, sir. Right. The statement was about the number of galaxies in the universe, and now I have to qualify what you mean by universe. The number of galaxies in the visible universe are of that order.
And is that an accurate figure?
No. So let me tell you how inaccurate it is. Had you stood there and said it was 1 trillion, I would have said okay. But if you had said 1 million, I would have said no, a lot more. There are many, many dwarf galaxies near the Milky Way that we've only discovered in the last couple decades. And so the universe is obviously, by extrapolation, full of small galaxies that are really faint that we've never cataloged. And with our new telescopes like the James Webb, we will see more and more telescopes. And so expect when James Webb is up, in 10 years from now, somebody will say the number of galaxies in the visible universe is 1 trillion or 2 trillion. But it's going to stay of that same order. Okay. The difference between 100 billion and 1 trillion doesn't bother me very much. Yes, sir.
About 300,000 kilometers
Second.
But does that matter which way it's going? What I'm saying is, what is the mechanism that causes the red shift if it's going the same speed no matter which way it goes?
Right. That question was, let's stay in a vacuum. The speed of light is 300,000 kilometers per second. What causes the redshift? And the thing that causes the redshift is the fact that the speed's 300,000 kilometers per second and can't be different.
But then if the body is going in the way from us,
Yes,
it's coming towards
it looks blue.
blue.
That's right.
What is the mechanism that makes the difference if the speed of light is exactly
Okay, the mechanism that makes the difference is the following. The speed of light is constant. If I've got a torch and I shine it out into space, it goes out at 300,000 kilometers per second. If I get on a high-speed vehicle or a plane and I fly in that direction at high speed and send out the light on the torch, it still goes out at 300,000 kilometers per second. My speed doesn't count. If that light's coming towards you, here come the waves. You remember the wave frequency? It's coming towards you. Here comes a wave. And the next one arrives sooner if it's rushing towards you. And so the frequency gets squashed. You're completely familiar with this. It's called the Doppler effect. And when a siren goes off, as they do here in Cape Town every few minutes, and you hear an emergency vehicle coming towards you, that frequency gets squashed.
sound is going to express.
No, the sound's not going at a different speed in the air. The sound speed in air is 343 meters per second. That doesn't change with the velocity of the vehicle. It's constant in air. It is. And so the change in frequency is just because of the compression of the wave coming towards you, the rarefaction going away, makes it higher frequency or lower frequency. It goes to the blue or the red. Now, the speed of sound in air is nearly constant. It doesn't depend on the speed of the thing that emits it. I'm going to take one last question from Lawrence, and then we'll quit, and I'll take private ones afterwards. Lawrence, or statement, whichever.
There's been some speculation that one day the Large Hadron Collider.
Oh, I'm having trouble hearing you.
Sorry. There's been some speculation that in the Large Hadron Collider at CERN, one day they'll be colliding the protons with each other and they will pop out mini black holes. What is your view of that?
If you heard that statement, there's speculation that when the energy gets high enough in a big particle accelerator, they may be able to produce mini black holes, and that's then followed on by the black holes eating the Earth.
No,